Everyone. I'm Sang Park of Kick, and today's speaker is Hyeoncheol Joo. He will be presenting on the topic of homomorphic encryption in quantum computing. Please give him a warm welcome. For questions, feel free to ask via Zoom chatting comments or through the microphone. And Hyuncheol, I kindly request you to read each question before providing a response. So I will give microphone to Hyuncheol.
Okay, let me start the presentation. Good evening, everyone. My name is Hyeoncheol Joo, and I am a member of QIC at Korea University. Before starting my presentation, let me briefly introduce myself. I am junior majoring cyber defense, and my current research interest focuses on improving the scalability of classical homomorphic encryption. I am here as a substitute speaker for this seminar, so I kindly ask for your understanding if the quality of my presentation does not fully meet your expectation. So I have prepared 3 chapters for today's presentation.
Everyone, I'm Sang Park of Kick, and today's speaker is Hyuncheol Joo. He will be presenting on the topic of homomorphic encryption in quantum computing. Please give him a warm welcome. For questions, feel free to ask via Zoom chatting comments or through the microphone. And Hyuncheol, I kindly request you to read each question before providing a response. So I will give microphone to Hyuncheol.
Okay, let me start the presentation. Good evening, everyone. My name is Hyeoncheol Joo, and I am a member of QIC at Korea University. Before starting my presentation, let me briefly introduce myself. I am junior majoring cyber defense, and my current research interest focuses on improving the scalability of classical homomorphic encryption. I am here as a substitute speaker for this seminar, so I kindly ask for your understanding if the quality of my presentation does not fully meet your expectation. So I have prepared 3 chapters for today's presentation. First, I will explain what homomorphic encryption is by
죄송한데 발표
introducing.
자료가 공유 안 된 것 같습니다. 화면 공유가 안 된 것 같습니다.
근데 그러니까 제 화면에는 보이는데 거기
혹시 잘
네,
보이시나요?
네, 지금 잘 보입니다. 감사합니다.
네,
네,
감사합니다.
감사합니다.
Um, I've prepared 3 chapters for today's presentation. First, I will explain what homomorphic encryption is by introducing classical homomorphic encryption to help you gain an intuitive understanding. Next, I will present a paper on the fundamental QHE scheme, followed by a summary of a paper that experimentally applies QHE. So, homomorphic encryption, hereafter referred to as HE, is a cryptographic system that enables specific computations to be performed on encrypted data without needing to decrypt it. One of the primary use cases is for clients to securely hide their sensitive data while utilizing services that process this data. The computation results are also encrypted and can only be decrypted and understood by the client holding the decryption key. HE can also be applied when the server wants to protect its model during the computation process. HE is categorized into 2 types, somewhat homomorphic encryption, and fully homomorphic encryption. Summa homomorphic encryption allows only one type of operation, either addition or multiplication, or limits the number of operations that can be performed on ciphertext. On the other hand, FHE, fully homomorphic encryption, imposes no such restriction and supports unlimited operations on encrypted data. The currently used HE schemes are known to be quantum resistant. This is because modern HE is based on lattice problems. A lattice problem involves finding the shortest vector that can be formed as a linear combination of given basis vectors in a multidimensional space. There are various variations of this problem, all of which are mathematically challenging and remain unsolvable even by quantum computers to date. In HE, the learning with errors problem is typically employed as the fundamental problem. So LWE shares the same mathematical security as certain lattice problems. The LWE problem states that given a pair B, A, where A and S are a vector of integer modulo P, which can be referred as vector of ZP, and B is an integer in ZP, and E is a small error, it is computationally hard to recover secret S. The LWE problem has several variations, among which I will introduce RLWE and MLWE. First, RLWE, ring learning with errors, is an LWE problem defined over rings. It uses a ring whose elements are polynomials modulo x to the n plus 1 with coefficients modulo p. Next, MLWE can be seen as an intermediate form between RLWE and OWE. In MLWE, instead of using vectors in ZP as in LWE, it employs ring vectors. I will explain a representative homomorphic encryption scheme based on RLWE. In this scheme, a ciphertext is represented as a tuple B, A. For a given script key S and message M, encryption is performed in the form B equals minus A dot S plus M plus E, where E is a small error term. During decryption, the inner product of B, A and 1, S is computed, which produces a value very close to the original message M. In the case of public key encryption, the public key is generated in the form of a ciphertext that encrypts the message 0. When encryption is formed in the following manner, decryption can be carried out in the same way as symmetric key encryption. Let me explain how classical HE applies operations on ciphertext in a way that corresponds to operation on plain text. For addition, you simply add the tuples. After decryption, the result will correctly reflect the addition operation. For multiplication, the multiplication of the decrypted plaintext introduces an S-cubed term. As a result, the ciphertext after multiplication contains 3 terms. At this point, a technique called relinearization is used to reduce the number of terms back to 2. During this process, part of the modulus is consumed. When further multiplication becomes difficult due to modulus exhaustion, a mechanism called bootstrapping can be used to restore the modulus, allowing continued computations. So classical HE has a wide range of application scenarios. First, in the field of privacy-preserving machine learning, HE has been used to implement models such as logic regression, PCA, and lightweight embedding models. It can also be applied to tasks such as genomic analysis and encrypted queries for LLM models. Second, statistical analysis on encrypted data can be performed directly on ciphertext. Third, it is possible to construct databases composed of HE ciphertext. Such encrypted databases can enhance LLM queries in RAG, which is Retrieval Augmented Generation systems. In this case, embedding vectors are encrypted and similarity computations are performed on ciphertext to retrieve relevant documentations. Encrypted databases also enable applications such as private information retrieval, where a client can query the database without revealing which element is being accessed, and private set intersection, where the intersection of two parties' datasets can be securely computed. Compared to traditional methods using Bloom filters or OPRFs, HE allows for a more intuitive structural design in these scenarios. In this section, I will introduce an efficient quantum homomorphic encryption scheme with flexible evaluators. This scheme was proposed by Chen and focuses on improving the flexibility and efficiency of evaluators in QHE systems. It allows computations to be performed on quantum data more adaptively while maintaining security guarantees. Let me provide a detailed explanation of how this scheme works and highlight its key features. The QHE scheme is built on basic quantum gates like Pauli and Hadamard gates, along with unitary matrices that define quantum states and operations. These are essential for encryption and evaluation in quantum computing. The scheme involves Alice, who holds a set of single qubit states and multiple evaluators, denoted as Bob. Using a combination of classical and quantum channels, the scheme enables secure quantum computations by applying specific operation on the qubits. I'll explain the details of how the scheme works, including the role of each participant in the following slides. In the key distribution phase, Alice generates private information by randomly selecting elements and defining a solution that satisfies specific linear conditions. She then transmits private keys to the evaluators, Bob, via secure channels. This phase establishes the foundation for secure quantum computation by ensuring that only the authorized evaluators can perform the intended operations. Next, the encryption process begins. Alice selects parameters and calculates an angle for encoding the quantum state. The qubit is transformed using a unitary operation, resulting in an encrypted quantum state. This encrypted state can then be shared with evaluators for further computations while preserving security. In the sharing and evaluation phase, Alice sends the encrypted state to the first evaluator, Bob1, while inserting decoy states for security. Each evaluator applies specific operations to the received state and forwards the results to the next evaluator. The final evaluator completes the computation and sends the result back to Alice. This collaborative computation ensures the privacy of the data throughout the process. Finally, in the decryption phase, Alice receives the result from the evaluators, which include the computed values and the final encrypted state. She decrypts the state using predefined operations and retrieves the expected results. This concludes the secure computation while preserving the privacy of both the input and the computation process. And this section highlights the experimental realization of quantum homomorphic encryption. Using photonics, the study demonstrates how secure quantum computations can be achieved. Let's explore its contribution and results. This work showcases two main contributions. First, a demonstration of quantum homomorphic encryption using an optical system, and second, the implementation of quantum works with single and multi-photon systems, showing secure computation in action. In this scheme, LS encrypts input states by applying polarization, transformers, and random rotations. Bob performs computations on the encrypted states without knowing the original input. Finally, LS decrypts the results to retrieve the computation output, ensuring complete privacy. Photon interference is key to this system. Identical photons interfere to enable computation, while orthogonally polarized photons do not interfere, preserving data integrity throughout the process. The experiment begins with photon generation through spontaneous parametric down conversion, and Alice encrypts the photons, sends them to the bulb for computation, and then decrypts the results. This setup demonstrates the feasibility of secure computation in a photonic-based system. And quantum works were performed with 1, 2, and 3 workloads across 4 paths using 2 unitary matrices. The results, compared to theoretical predictions, showed strong agreement, proving the reliability of encrypted quantum computation. So privacy analysis reveals that increasing the number of polarization bases and optical modes enhances security. The guessing probability decreases significantly as optical modes grow, ensuring robust privacy protection. So this is my presentation, and thank you for listening to the presentation. While I don't specialize in quantum studies and may not have all the answers, I'll do my best to address your questions. And please feel free to ask anything. Thank you.
Okay, so if anyone have any question, then you can use Zoom chatting comments or microphone. So I think there is no question. So
There is one
uh,
question from EQUIS.
from case. Oh, okay.
이해가 약간 제가 잘 못해가지고 그런 건데, 처음에 그 호모몰픽 엔크립션이 그 암호문을 결국에 함수 처리해서 다시 그 나온 그 새로운 암호문을 다시 풀었을 때가 원래 함수를 그냥, 아니, 원래 그 문장을 그냥 함수 처리한 값과 똑같다는 건데 여기서 나중에 퀀텀 호모몰픽 엔크립션에 대해서 설명하실 때 그게 약간 원래 그 고전적으로 사용되던 그 호모몰픽 엔크립션 그런 방법하고 좀 어떻게 연관돼 있는지 잘 이해가 안 돼서 질문 드렸습니다. 그러니까 양자에서도 이 동형 암호문을 만들 때 약간 원리가 어떻게 되는지 조금 더 설명이 해주실 수 있는지.
네, 이제 대략적으로 설명해 드리면 이 그림에서 보시는 것 같이 이제 앨리스는 이제 phi m 스테이트를 가지고 있고 이제 어떠한 이제 연산들을 이제 여기서는 이제 연산을 D명의 밥이 해주는 상황인데 이때 이 밥은 각각의 유니터리 연산들에 대해서 이제 분산된 정보를 각각 가지고 있습니다. 그래서 어, 앞서 설명드린 클래시컬 홈오피 인크리션이 개념이 있지만 여기서는 또 추가로 이제 멀티파티 컴퓨테이션의 개념이 약간 들어가 있는 것인데요. 그래서 각각의 밥들이 이제 주어진 조금 변형된 유니터리를 계산하면서 이제 최종적으로 음, 앨리스만 알아볼 수 있는 이제 최종적인 어떤 스테이트를 반환받게 됩니다. 그래서 앨리스는 이제 자신이 가지고 있는 키로 이제 스테이트를 디크립트해서 어, 원하는 연산 결과를 얻을 수 있다는 것을 설명드리고 싶었습니다.
감사합니다.
네, 감사합니다. 또 추가적인 질문 있으시다면 해주시면 감사하겠습니다. 쓰시다면 이제 발표 마무리해도 될까요?
Yeah. 네. I think there is no more questions. So, um, yeah, I think many of you, and including me, may have been introduced to the field of QHE for the first time. So, thank you, Hyeoncheol, for providing such an excellent introduction. So I think we can finish the seminar here. Okay, thank you.
Thank you very much.
수고하셨습니다.
네,
감사합니다.
수고하셨습니다.